trying to ask.
Okay, I realize I stand between you and Station 53, so I'm going to try and make this as painless as I can. But I want to talk about some of my experiences with...
Hey, I'm sorry, Jim, can you talk into the microphone, or maybe somebody give you a mic? Sorry.
Sorry, is this better?
Yeah.
Okay, great. Yeah, I wanted to talk about some of my experiences, relatively recent in building agent-based systems, and come out from that with some suggestions for inverse generative social science and where we come. I've got a background in AI, but I started using agent-based models about 6 years ago when I switched to the Cybersecurity division where I work at USC Information Sciences Institute. And the reason for that was I looked in there and sort of thought, what can I do to best improve the situation in cybersecurity? And at that time I found people were working a lot on nice models, on clever tools, firewalls, and starting to use machine learning to recognize intrusions. But individuals were not using a whole lot of that tech. In fact, if you put a cybersecurity system in place for somebody, they might well actively destroy it. Or they might use it incorrectly and believe that they're safe when they're not, which is more dangerous than not having it in some cases. So I wanted to look and try to understand the situation under which this happens and see if we could actually sometimes predict this and start to build policies that are going to work better from the get-go because we have a better idea of how they'll be used in the real world. So this is one motivating example that I looked at the time. I apologize if you've seen it before. This is the situation in a nurse's ward. Around about mealtime, the nurses have to go and give pills to a whole lot of different people all around about the same time. And in this particular location, they had a number of shared workstations. And so a nurse would go up to a workstation, log in, bring up the spreadsheet for their patient, see what the medication ought to be, take the medication to the patient, give that, go back and put into the spreadsheet that they gave that medication to that patient and everything's good and move on to the next patient. But this is a really busy time. So while they're gone out to that patient, another nurse comes along, there's no free workstation, they log somebody out, that nurse, they bring up their spreadsheet for their patient, and then they go off and start to give their medication. The other nurse comes back and enters the wrong medication for the wrong patient because maybe they didn't notice that they got logged out and it's a different spreadsheet. And this can be very dangerous. So the people there looked at, well, what can we do? And they hired a consultant. He brought in this great cybersecurity solution. This is a kind of a security issue, although there's nobody really trying to break in here. And he put in this proximity sensor for auto logout. So you go in there, you start to do your work. As you walk away from the workstation, just as I start to be inaudible, I guess, you get logged out. And then when you come back, you'll find a logged out, you won't find anybody else logged in. You can go in and you can get back to where you were and you can put this in and this problem is solved, right? So guesses, I'm sure, as to what happened when he came back 2 weeks later to find out how his solution was working. It was basically a number of styrofoam cups put on top of all the proximity sensors and disabling them, turning them off. So our question was, well, could we have predicted this? Could we use an agent-based model to get ahead of this and to understand that this is going to happen? Could we possibly think of a styrofoam cup in some agent-based model of nurses in this arena? And I contend that no, we couldn't, but we can build some general approaches here that help us to get a lot further into understanding what's going to happen and to build, help build policies that are more understanding of the real world. And some of the general principles that we put into our agents to help us to understand this, one of the understanding the importance of tasks and timing in a workflow. In a lot of cases here, this is an example of an organization. They're going through a workflow, and there are some points when there are some real time crunches with the little stopwatch at the end there, so I can't go over and point at things from here. So you have a lot of tasks to do in a short amount of time. If you put in some solution that creates pain at that point, it's going to be viewed as very painful, and it's probably going to be taken out. And so the next thing is that it's important to understand the perception. So as people were saying yesterday, it's not necessarily the reality, although the reality here was probably painful, but it's the perception of the cost of the new action for the individuals versus the perceived benefit, which may not even be clear, and there are various cognitive biases to say, well, yeah, other people may have put in the wrong medication for the wrong patient, but I never do that. And then another part for building this model is to just appreciate the creativity of humans. So we could not, in our model, find and represent the styrofoam cup, but we don't have to. We just need to say, once you've got that much pain, humans will find a way. They'll find a way to turn this off. And so I have another picture here illustrating the beauty of this, and also illustrating that the fourth part is diffusion of innovation. So what happened, probably one bright spark put down the cup, and then everybody else saw it, and they all put down the cup over their system as well, or maybe one person went all the way around. The picture here is a beautiful wooden box somebody made to hold their mouse. And you put your mouse in it. It also has a little hole in the bottom where you put your mechanical watch, which ticks every second, jogs the mouse every second, and makes sure you never get logged out for inactivity. The beautiful thing is the boss comes back and he just sees you put your mouse in a nice wooden box. Fine, you know, he doesn't understand that you're circumventing the security regulations. Diffusion of innovation, because I got this off of a YouTube video explaining to us all how to make beautiful boxes such as this, so that we don't have to get logged out, which of course is another security hazard. So there's a lot of creativity, diffusion of innovation, but some general principles that we can use to try to capture these situations and make them better for people. So I went ahead and built an agent-based system around this and built my own cognitive agent platform. That was possibly an irrational decision, but it turned out that in the long term. And this looks quite similar to ACTAR and SOAR, which I was aware of as I did this. You have a dual process model, so at any time the agent takes in its perceptions and can make actions based on two different processes, an instinctive one that comes up with an action straight away, and a deliberative one where we added support for people to build models that used reactive planning techniques and mental models using forward projection, so that we could sometimes model the amount of time it takes for somebody to think of or to remember or imagine a certain solution. Yeah, so one important difference, though, between this and something like an ACTAR or SOAR, particularly a SOAR version, is that we didn't have this tied up to universal learning. One consequence of that in SOAR is that very often the instinctive part is really just doing exactly the same as the deliberative part, only much, much faster. But that's not what we saw with humans. In particular, for example, looking at phishing experiments. But it's experiments where you'd sit somebody in a lab and say, do you think this is phishing email? And they'd do a job at some level. I won't say good, but they'd do a job. But then you send them the isomorphic, the exact same email, when they're going around and doing everything else, and they'll be fooled every time, because they're using a different set of rules, which actually leads to a different set of behaviors. So we put this system together, and one thing it helped us to do was to find some of the examples where we believe we have security, or we're doing something for security because we live in a world where we're thinking about the people around us. But actually we live in a networked world where there's lots of other things going on. So this is an example of what we call an uncanny valley, so a surprising dip in security. Imagine that you're running your website, and people are logging on, and you want to make it more secure to people logging on by being hacked, and then your website being hacked. So you turn up the security rules, you make them harder, and we've seen this happen on many of our sites. So suddenly you need 8 characters, and you don't just need an uppercase and a lowercase, you need a number, and you need a special character, whatever that is. So what we found was that if you do this, you get to a point where as you make your system more secure, it actually becomes less secure. Sorry, as you make the passwords tougher, it becomes less secure. And that's because it begins to interact with two things, with the coping mechanisms of humans and the network world we live in. So first of all, humans have to remember scores of passwords these days. And we use the Levenstein distance measure that somebody else mentioned earlier as well to calculate the pain of remembering many, many passwords, which are often mostly quite similar to each other. And what we found is that if you make your password the toughest, that's the one they're going to copy onto all these other sites. So now your security is tied to the security level of all these other sites that are using it, because once they're broken into, the hackers know that you've probably used exactly the same ID and password on other sites, and they'll try that out. So we were able to capture that. That's good. And then as we started to look at validation issues here, we went through, I'm sure, issues that everybody here has gone through as well and has looked at. But how do we represent and think about the set of parameters and the set of descriptions of the world as well as the agents that we need to go through to build an experiment, to build a set of trials? And so I built a system that actually makes that visible to the system itself. So the tool that's running your agent-based simulation has an explicit representation that it can look at of the experiment itself that has independent and dependent variables, that is going to consist of a number of trials, and there's going to be a set of rules for setting up the experiment for each trial, and for talking about how you set up all the agents that are going to be in the trial. And each of the parameters, which both belong to the world rules for the trial and to the agents, allow us to represent to the system something about the distribution of possible values, also the range of values, and in some cases, a link back that goes to the empirical work that led us to put that set of values in there. This is more useful for somebody else that then uses our system and looks at results that maybe don't make sense to them and can go back and say, oh yeah, this was based on 15 master's students at USC, and that's why it's not really working for me in my situation. So one example of what we can do with this is an example of building up a cybersecurity attack and defense situation. The red guys on the right are the attackers. I'm going to talk about them using phishing, but they're planning agents that can use a variety of different attacking strategies. The green guys are going through their workflow in their organization. And we actually used this as a human subject experiment. We were looking at teams of defenders who had to defend the green guys against the attacks coming in. And what they didn't know was that as they were sitting in Arizona defending this system from their computers, they were actually VPN'd into our testbed in Los Angeles with networks of hundreds of computers using SDN, very similar to other testbeds, so that we could see how this was working out and we could see how our agents were doing. But they were autonomous at this point. And they actually found that this was one of the most realistic experiments they had had because the agents could do their own planning. I'm starting to. But what we had here was a representation inside of this of the important parameters, like the probability that each agent is likely to identify a particular email that gets as phish, the probability that it will open attachment if it doesn't identify it as phish. And the system itself could help us and make it easier for us to look, for example, and look at the number of hits of malicious software that gets opened as a function of the number of phish emails, but also as a function of the probability distribution here. And it could go further and help us to look at, well, there's this other parameter talking about the rate at which you forward emails. Does that matter? And we can see, at least from this experiment, that it doesn't really matter as long as your agents are fairly decent at recognizing phish. But if they're not, then that's actually going to exacerbate the problem. And you might want to start a policy: don't forward an email to somebody else if you're not really sure about what's in there. And it also makes it easier for us to take in other information. So the IT department comes and says, well, the last time we had an attack, there were between 5 and 7 successful hits. How does that help us to build a better system? Well, we can go back and we can look through the probability of each different configuration of parameters that would guide us to that. And then we can use that to resample and hopefully come up with a set of predictions about the other elements of this simulation that are going to be closer to reality. So these are things that we can do with a more explicit and machine-readable representation of the different parameters, things that you've probably looked at as well. So then we took this, and I think other groups here have been talking about the Social Sim DARPA program, and this is what I've been redeveloping this toolkit for lately, and it's been a great experience and a good chance for me to look at using large amounts of data and finding ways to build up these agents semi-automatically from the data and see what we can do with that. So the aim is to build this virtual laboratory to look specifically at micro to meso to macro and in other directions as well in that. As part of that, we needed to build a simulation that had about 10 million or so Dash agents in one model, but that was not too much of a problem with this particular architecture. Typically, we don't need more than, well, lately we don't need more than about 100,000, and we can run 6 million on one machine, which is a whole lot faster than having to run a distributed process, which we need to go larger than that. But the basic task that we've essentially been handed in this is to take large amounts of data on a particular social platform, and later a larger number of social platforms, that encapsulates what's happened over the last few months, maybe over the last year with a gap, and then say what we think is going to happen in the next couple of years. So what we'd like to do is build our agents to essentially make use of the data that we have. We have data on individuals and their performances and what they've been doing, and use that to predict what's going to happen next. So in the last one of this, we're looking at about 70,000 agents, but working over multiple social media platforms. So this is actually still a very, very constrained environment. So we're able to build a way here to use the data directly to help us to build up agents with machine learning techniques that, again, I think a lot of other folks have used here. So what we did was we built a system that was almost as empty as possible. This is still a Dash model, and so it has access to the dual process, to the different sets of cognitive limitations built into it. And then it has access to a small number of actions it can take on each of these different platforms. It can tweet or retweet, it can post a Reddit message or post a comment on a message. And we built an architecture where the world itself captures this notion of information curation that folks have talked about. So as the agent looks at its world, it's only going to see a certain subset of the messages, initially based on recency, that are available to it. And we provided some machine learning techniques to just answer the question of, will the agent tweet or retweet this particular message? Will they post a comment on this particular message in Reddit? And the agents use this, and they look at all the messages that they have, and then they decide maybe to make one tweet or retweet, or maybe make a set of tweets that go beyond the current threshold, and to use it in that way. So this is a very simple piece. I'm just going to talk now about some of the things that we learned out of this. One thing is, I think we've been talking a lot about the different machine learning methods that are available here, and people have used a variety here today, and I think that's great. I think that talking about the features and the way we build the feature space for machine learning here is at least as important as the method that you use. And so I think we used one version here that might be quite applicable to a lot of agent-centric methods, as we're starting to use machine learning within an agent-centric world to do some of that dimensionality reduction that we've talked about. So what we had in this particular world is we had, maybe up to in the order of tens of millions of agents, but maybe a lot less, maybe between hundreds or thousands of features for each agent. But often the information for one particular agent is very sparse. These social media platforms are growing all the time, which typically means that half of the agents you see haven't been there very long, and we don't know very much about them. So we can't just learn a different model for each individual agent, because we're going to find we don't have enough information for some of these agents. So what can we do? Well, what we did here is we turned this into, we created extra features which are indexable functional features. So they're looking from the agent's point of view at the world around it. So as well as all the information about the tweet, when it arrived, what time of day, what's in it, we have information, this tweet is from someone that this particular agent retweets regularly, yes or no. This post aligns with the agent's most commented posts in some sort of word-to-vec model. That means it has topics in it which seem aligned with the kind of topics that turn this particular agent on. And maybe this agent has exceeded its own typical length of a Twitter session at this point, or not. So these get added into the set of other features, and we basically we rerun these features across the whole model, and then we run with those pieces. And this worked really well for us in one particular set. Sorry, there's way too many different metrics here that we sort of have to provide for DARPA, so I apologize for that. But it shows that we're able to capture pretty well the rate at which information might jump from one platform to another. Whether or not there's a correlation between the number of agents who are talking about a topic on one platform and talking about the topic on the other platform. We can also find if there's a sudden burst, so suddenly a lot of people are talking about one particular thing, we were able to predict pretty well how many people would be involved in that and for how long, and how long that piece of information would stick around before it disappeared. And the main thing is, for most of these things, we did better by using these machine learning models that I talked about, significantly better than we did by just using statistical techniques, or by using what we called here the random null model. The purple one is really just taking the past, replaying it as the future with a little bit of shuffling. And honestly, I think other teams on this program like us found that hard to beat quite often. Okay, so I'm going to make a couple short observations about that. I think as we move towards like this inverse generative model, where we're more and more interested in having agents that are supplemented by our understanding of data, or that are built automatically from a representation of the goals that we want this agent simulation to have, it's going to be even more important to have a machine-readable representation, as we did here, of the assumptions. So the system, you can never run a simulation without the system itself being able to examine its simulation and tell you whether some of the parameters don't seem to be of any value, and give you hints about what you might be able to reduce. It's also important to design these open agent models. So one thing that helped us a lot in our system is it was very modular and composable. We could basically use software engineering techniques to take versions of agents and change them very rapidly, to combine two agents, so we had something that was that combined those two particular values, or to say to one, do less of this, do more of that. And therefore, it's also important to be able to design your agent not just to do the task you think you're designing it for right now, but to be available to be there for a wide variety of tasks, and to be open to change, to be able to be changed. But that's all probably motherhood and apple pie to people here. I think I have enough time to go into one other piece. I'm going to make a quick suggestion of some techniques that might be useful to this community. based on some things I've done before. I really liked Ivan's talk. When he was talking, one thing that in particular I thought was good was the idea that you've got to have human in the loop. That as we do this, we're not going to have a system where, we let these agents build themselves and then just we stay out of that for the whole model. We want to be able to understand the principles under which these agents have been built, and it's important for the experts to have come in and lay those principles down to begin with. But I think that we can actually find ways to smooth that, to make that path a lot more quick, and to actually use AI to help us to make a better connection between the experts and the system that they're building. I think Josh mentioned earlier that he looked for inverse Turing machine work and didn't find much. I think you'll find a bit more work on programming by demonstration, programming by example.
Great.
And one thing I worked on about 10 to 15 years ago was programming by instruction, which is a slightly different technique. It's again based in the office world. We're trying to make life easier for people who are dominated by algorithms, these crazy algorithms. And so this is one where there's some program that's telling you what you need to do to purchase a laptop. And it's the larger the organization, the more rules there are, right? So you have to get a requisition form, you have to submit it, you have to get authorization to purchase this laptop. You probably have to get a certain number of laptops as the organization from minority-owned companies. All of these things have to be met. So then, if somebody's made a mistake in this, or somebody's downloaded this program from some other organization and brings it to you, you want to yell at the program. You want to say, no, I don't need authorization if the cost is below 2,000. What are you doing? Turn this off. So we made a system where you could do that. You could say, you don't need authorization if the cost is below 2,000. And our tool would search through the space of possible modifications of this program to come up with a bunch of new candidate programs that would actually match that description. And it can do that without necessarily knowing too much about the underlying programming language. Of course, we have to have a grammar that's going to generate this language for us. And we have to have a technique that generates an English description of the program, which is what we're looking at here anyway. If we can do that, then we can search through the space of possible modifications to find one whose English description closely aligns to the description that the user said. And then if we can do that, we can say, oh, you probably mean the total price of the selected laptop we're talking about can be less than 2,000. If it is, then this authorization step is going to be conditional. And then the tool can tell us, well, if you do that, you break the program, because there's this later step that needs this authorization thing as a precondition. So let's talk about maybe relaxing that in that step and making that easier. So anyway, this was some work that was done, and there's been a lot of work since then in this area. And I believe that we can use this here to help designers who are working with a simulation to not just lay down the rules and then look at it and then come back later and see what worked and what didn't, but to say, no, hey, this is not what I want you to be doing. You should be doing this slightly different thing. And have the tool say, oh, the only way I could do that was if these agents were behaving in a different way, or if they didn't come on until later. Is that what you want to do? Do you want to try that? Or we could come up with a set of different options to allow people to much more rapidly interact with the system that they're building. So that's just one suggestion here. I don't know if I'll leave this up, or maybe I'll go back to these other set of observations and see if there's any questions. Thank you.
So I've really found it hard to figure out how to tackle social engineering in cyber. And I know that you're close to that. When you're obviously thinking about that when you talk about phishing and emails. There was two things I was curious about. One was this notion that you drop the USB key with all the information that says salaries on it in the parking lot, and no one can resist picking it up and putting it in their machine and infecting their machine. And then the other one was that it's not really social engineering, but it's another restriction that I think some of us have found in the defense community, which is when you get your clearance number, you have to give them like a 12-character password, and you're not allowed to write it down there, and you can never store it on your computer in your vault.
Yeah.
So if you're someone who's using all these password protections through your vault, you're actually not allowed to do that. And so it's beyond anyone who doesn't use that every day not to write it down somewhere. And I was just wondering if you had thought about behavioral models and dealing with that kind of social problems around security and social engineering for security.
Yeah, so if the question is, am I tilting at windmills and trying to help where things are beyond everyone, then yes, I am, and I don't necessarily know there's a good way around all of that. But there are certainly ways that we can help with that. one thing I'm very interested in, also, a guy earlier was talking about nudge methods that we can use, and so we can use nudge methods here. And we can look at, one thing that I thought was helpful about the techniques I'm using is they're not necessarily trying to change human behavior. They're trying to build something that works better with human behavior. I think, we studied a number of different organizations when I began doing this, and I can tell you that the ones with the worst security were the military because they had the tightest security. And so it's exactly what you'd think, right? You have an intern, for example, or as you're saying, you have to remember these impossible passwords. You have an intern who comes in to work for the summer. He's not going to be able to get an ID and an account in the course of just 6 months. That just doesn't happen. You have to go through all these checks. So what does the intern do when he needs to get information, that he can use in his work? Well, he taps into the Wi-Fi in the Starbucks across the street because he's, solving problems and getting his work done. And so he's just destroyed all the security of this network because of this sort of pseudo-security. I think as we make that more clear to people, then you get a chance where you can change this and make things more reasonable. It was very heartening to see, just a few years ago, that the government policy about passwords, they're actually saying, don't actually make people change their password every 3 months because nothing good comes of that. Yeah. So there's beginning to be more understanding of this. And really, it's just one example of many that people have talked about today where we basically need to understand better how people are reacting to these technosocial systems we're building and make them so that we can respond better.
Do we have to solve all of those on a specific use case one at a time? Like your nurse observation was, one is that it's going to be ingenuity to actually keep people. People will be very ingenuous in order to figure out how not to be auto-logged off. And then there was also this piece of, well, they're not going to want to do that. And so I was just wondering to what extent you think that generalizes in security cases.
Yeah, that's a very good question. I mean, I'm sticking with my assertion that being able to spot the problem does generalize, that you can find these pressure points through workflow and through understanding perceptions. And so those also become the points where you can attack it. So you can try to deal with perception, or you can be draconian. Well, I remember one guy who was in charge of security in the New York Stock Exchange was very pleased with himself because people were walking away and leaving their computer unprotected, and there seemed to be no way he could stop it. He also heard that people had their passwords tapped at the bottom of their keyboards, and so he went down one night and turned them all over. And yes, their passwords tapped to the bottom of 30% to 50% of the keyboard. By the way, that's one thing you can do in the New York Stock Exchange that you can't do in most organizations. At 5 o'clock, everybody's out because there's nothing more you can do. So actually you can do things like shut down the whole system, which is brilliant for getting rid of a lot of issues, but you can't do in other organizations. What he did after that, though, is he said, okay, new rule, if some trade that goes south was made from your computer, it's assumed that you're responsible. And all of a sudden, a lot of people started to log out, they didn't put their passwords there, and they kept much better security. But honestly, I don't believe that kind of draconian rule is something that you could ever get away with making in most cases. And it's going to, in long term, probably make you the enemy of the people you're trying to help. And it's more about trying to build a case where you see yourself as, I don't know, this sounds dumb, part of the same team. I don't know quite how you get to that point when you're really doing things that cause people pain. But we have to help people understand more of the consequences. I worked with Jean Camp. I made some real fun adverts. So she mostly came up with the adverts, but we put them out there. One was, okay, you pick up a USB stick off the floor, and you're going to stick it in the thing and do what you like. So the next day, of course, you see a piece of gum that's on the floor, so you pick it up and put it in your mouth, right? It's about the equivalent, so why wouldn't you do that? And then help people sort of have that image as they pick up a USB stick.
I do have some thoughts on, so I do think that we should almost never try and solve for these problems that are on the edge cases, right? That there's always going to be, a 1% that we may not be able to account for to a large extent, right? And I think that also gets back a little bit to what Rob was saying earlier today about no one ever tries to model the individual at the individual quantitative level, right? That trying to model exactly which person is going to put the styrofoam cup on top of their thing first, I think is a fool's errand, right, to some extent, right? And so I wonder if there is a level to which we could, draw a bound around that and say, this is the space where we are reasonably certain people are going to look into, right? set of behaviors that we could anticipate, and that we should. I mean, when I do intro to ABM, one of the things I always throw in there is I do a picture of this is how long I've been teaching it, Kim Jong-il at one point, right? And I say that you know that there's no use of using agent-based modeling to model his behavior, right? That like I'm trying to figure out what that person is going to do and how they're going to affect global politics from a point of view of agent-based modeling. It's not necessarily worthwhile because the behavior is erratic, idiosyncratic, not necessarily useful, right? On the other hand, I do always mention as a caveat, if instead you are interested in modeling the behavior of a group of despotic dictators, right, and what they might do, right, in the general case, and then on average over the course of the next 10 years, right, that might be something agent-based modeling could help you with, right? But I think that there's a lot of other modeling approaches that might be more suited for detecting that someone's going to put a styrofoam cup on top of their proximity detector, such as ethnography, design engineering, right? These kinds of approaches that aren't agent-based modeling. So I'm a big fan that agent-based modeling doesn't have to, replace all those other approaches, right? We can use insights from them to guide our work, right? But we don't have to supplant them in any way.
Yeah, that's a very good point. So I'm proud of your great experience about where ABMs provide something that simple ethnography could not have done there. I do wonder, though, about an ABM that would tell me somebody launched nukes in North Korea. We're not going to say who. Our models do have to sort of pick one agent that's going to put the styrofoam cup on there.
Yeah, and
we just don't get. That's not really the output that we want to be judged.
Right. And yeah, it is a fine point I'm trying to make there, right? Like it's so. Trying to remember his name. There's a guy who was graduated from University of Michigan with me who did models of closed regimes using agent-based modeling, right? And so he would model power dynamics in those without names, without people attached to them, right? But rather just say, here are the power dynamics that normally exist in these kind of regimes, right? Here's the kinds of things they might do. And so exactly right. His model, one of the outputs of his model would be someone's going to launch nukes, right? But it wouldn't predict that Kim Jong was going to be the one who was going to do it necessarily, right? Or that he would decide to meet with Trump, right? Or anything like that, right? Like those kinds of things would not be predictive outputs of this. It would be that there might be an incentive to reach out to the West, right? There might be an incentive to, who would do it would,
So, but I think at this level it's a modeling issue, right? I mean, essentially it's the same model, you just took the names off. And so if I leave the names on, but then say I don't really care who it was,
right.
It might be the same. But it's nice to build that into the model, that the level at which.
Right. I guess we could say that there are. I don't know how to put this exactly. There are some behaviors. I mean, the model. I don't think his model would ever say, like, it's behaviors at the absolute idiosyncratic level, right? Like it's the fact that. I don't know enough about North Korea to come up with an example there, right? Necessarily, right? That like maybe he has they do those mass dances, right? So maybe he has them perform on the left side of the stage versus the right side. Like those kind of predictions are nearly impossible to make.
Yeah.
The predictions that yes, they want to be open to the West, yeah, that's possible to make. The prediction that they want to be an aggressive action toward the West, yes, that's possible to make, right? It's the kind of individual level.
I mean, I think that is still something where there's still usefulness to build. We were thinking of building agent-based platforms in risk management to sort of, you create the general sea of operations in whatever system you're doing, and then you're going to drop in, you as policymaker, drop in these wild data points. You're going to drop in Kim Jong-il or something. Right. So that comes from that's the exogenous shock, but there's an agent-based model to understand how the system's going to process that.
Yeah, definitely. And you could definitely model how the system would react to those kind of events. That I fully.
Right, but it's always in risk management. We often think that the policymakers are going to think about the tail. They don't get all of them, but.
Okay, well, I think that might be a good place to wrap up for the day.